This is the last question of the last assignment. To see if students with longer feet tend to be taller, a random sample of 25 students was selected from a large high school. For each student, x equals foot length and y equals height, both in centimeters, and they're recorded. We checked that the conditions for interference about the slope of the population regression line are met. Given is a portion of the computer output from the least squares regression analysis using this data. There's the table, classic computer output. So which of the following is the best interpretation of the value 0.4117 in the computer output, which is there circled. So we have A, the linear relationship between foot length and height accounts for 41.17% of the variation in height. B, in repeated samples of size 25, the slope of the sample regression line for predicting height from foot length will typically vary from the population slope by about 0.4117. For each increase of 1 centimeter in foot length, the average height increases by about 0.4117 centimeters. D, when using this model to predict height, the predictions will usually be off by about 0.4117 centimeters. E, the linear relationship between foot length and height is moderate and positive. So let's get into this. Let's look at E first. The linear relationship between foot length and height is moderate and positive. Well, let's find the well, this is talking about like what would the slope be, right? So if you're looking at a slope like this would be, okay, hold on, that's a bad example. Okay, so imagine a scatter plot. That's basically what it's talking about. The positive can be found from what angle it's at, and moderate, severe is like light. I don't know. It's moderate, severe. It doesn't matter. But basically it's saying the data is like kind of together and positive, so it's pointing up. So let's find the coefficient for the x, which will give us the slope. So let's look at this intuitively. So the number that will be in front of x is going to be a coefficient, right? So it's going to be either this or this. It's not going to be standard error because, well, it just won't be. So we're going to look here at foot length, which is x. It says so in the question. It's the well, this is the response variable, this is the explanatory variable. So we have the explanatory variable here. You can just label that x. Okay, so because of this, we can see that the x value is going to be 3.0867, which is not our special number here, so you can cross that out. D, when using this model to predict height, the predictions will usually be off by about 0.4117 centimeters. So looking at this, when using this to predict height, that's our y value, the predictions will usually be off by about 0.417 centimeters. Well, we're going to look at standard error because it's talking about, you know, the predictions will usually be off. That's a standard error. So we're going to look at standard error, but it's not going to be the x value because it's talking about height, which is the response variable, which is, you can label that like that. So with this information in mind, you can see that the number for answer D would be 10.2. So when you're predicting height, the predictions are usually off by about 10.2 centimeters. So we can cross that out. For each increase of 1 centimeter in foot length, the average height increases by about 0.4117 centimeters. Well, we've already kind of talked about the slope here, which is 3.08, so that is not the correct answer, because for each increase of 1 centimeter in foot length, that's for you go one across, how much are you going to go up? It's not 0.4, it's going to be 3.08, right? So you can get that slope right there. It just keeps going, right? Get the idea? So that's talking about the coefficient for the x value, which is going to be the slope. So let's just jump over to A. The linear relationship between foot length and height accounts for 41.17% of the variation in height. Well, this is gonna be the linear relationship between foot length and height accounts for 41.17% of the variation in height. Between foot length and height. Oh, I see. Okay, so this is talking about the relationship between foot and height. It gives us a number and it tells us variation, which is important. Well, also I didn't talk about this in letter E, but if you look down here, R squared, that tells us the strength of the relationship between these two variables. And R squared tells us there's 72.8% is well, moderate. It's a moderate standard error. It's a moderate variation, sorry. So that also makes E disqualified, because again, that's not 0.4117, that's R squared. And this is also R squared because it's talking about accounting for the variation in height, so that will not be our magical number. So moving on to B, in repeated samples of size 25, the slope of sample regression line for predicting height from foot length will typically vary from the population slope by about 0.4117. Well, this is the standard error of our x value. So, and it's talking about slope. So let's say we have our population slope, right? Let's make a little graph here, like this. Sorry. In repeated samples of size 25, it's going to vary because not all samples will give the same result as the population. So let's just, add in a few lines that are like this. So on average, there can be 0.4117 x to the left or to the right. Right, not much, which is why it's a pretty high correlation. Well, moderate, but pretty high. So looking at our standard error coefficient, looking at our x value, that tells us exactly the slope for the sample regression line for different samples is going to have this variation. So the answer is E. There you go.